It is 4:47 in the afternoon on July 19th, 2023, in Phoenix, Arizona. The thermometer at Sky Harbor Airport reads 119 degrees Fahrenheit. The city has endured 20 consecutive days above 110 degrees, a streak that will eventually reach 31 days. The power grid is straining. Maricopa County Medical Examiner has already launched 425 heat death investigations this summer. In a modest stucco bungalow on the west side, a woman stands on a kitchen stool holding a roll of silver film in one hand and a tape measure in the other. The total cost of what she's about to do is $3.14. 90 minutes of effort, and by sundown, the south-facing bedroom will be 18 degrees cooler than the room across the hall. No air conditioner, no fan, no electricity from the wall. She is applying a technique first measured nearly 2 centuries ago in a small Italian laboratory and, for reasons beyond physics, largely forgotten. To understand why it works, we must go back through almost 200 years of carefully observed, then overlooked, knowledge. The year is 1830. A man named Macedonio Maloni, 32, trained as a lawyer in Parma, has abandoned law for physics. For the past 2 years, he and a friend, Leopoldo Nobili, have constructed by hand the most sensitive heat detector ever, the thermomultiplier. A row of solder junctions between bismuth and antimony, wired to a galvanometer, moves its needle when a candle is lit. Within a year, the failed revolution across the Italian peninsula will strip Maloni of his university chair and force him into political exile in Paris. In 24 years, cholera will claim his life in a small town outside Naples, leaving the second volume of his work unfinished. But tonight, none of that has happened. Maloni leans over his bench, preparing to prove what the leading physicists of his day deny. He will show that radiant heat, the warmth from a distant fire or the sun streaming through a window, is not a substance flowing between bodies. It is a wave, capable of reflection, refraction, and polarization, acting almost like light, differing only in wavelength. When he positions a polished silver sheet between his lamp and the thermomultiplier, the needle barely moves. Most of the heat has bounced away. He records the reading, swaps the silver for polished tin, then copper, then gold, noting each result. He submits a paper. In 1834, the Royal Society in London awards him the Rumford Medal, the highest honor in heat research. And then, gradually, the world forgets. About 30 years later, in a Royal Institution basement in London, an Irish physicist named John Tyndall picks up a similar thermopyle and takes the work further. He measures how gases like carbon dioxide, water vapor, and methane absorb the same radiant heat that Maloni had reflected from polished metals. His 1859 paper opens the door to what is now called the greenhouse effect. For our story, what matters is that Tyndall establishes Maloni's key finding. Polished metals reflect radiant heat. The results are repeatable, verifiable by anyone with a thermopyle. Through the 19th century, aluminum remains more precious than gold. At one point, Napoleon III serves his most honored guests on aluminum plates, the lesser on gold. That changes in 1886, when Charles Martin Hall in Ohio and Paul Héroult in France independently invent the electrolytic process. Aluminum prices plummet by over 95% within a single generation. By the early 20th century, aluminum moves from jewelry to wire, then sheet, then foil. In 1919, a Virginian named Richard S. Reynolds begins rolling tin foil for cigarette and candy companies in Louisville. By the late 1930s, Reynolds Metals sells foil laminated with craft paper for building insulation, marketed to farmers and rural builders unable to afford fiberglass bats. World War II interrupts. Aluminum is diverted to aircraft skins, ration packaging, and radar countermeasures. Reynolds lobbies for federal aluminum capacity, opens new plants in Alabama and Arkansas, and his company becomes one of the largest aluminum suppliers of the war. In 1947, peacetime surplus allows Reynolds to release consumer kitchen foil, now common in pantries, while radiant barrier paper fades from public awareness. The idea jumps to orbit. In 1964, NASA engineers, facing extreme temperature swings in low Earth orbit, roughly minus 150 degrees Celsius in shadow, plus 120 in sunlight, develop aluminized polyester film, branded as Mylar. That year, Echo 2, a 135-foot Mylar balloon, launches as a communication satellite. The same film, cut smaller and folded, becomes pocket-sized emergency blankets NASA provides to recovery teams. By the late 1970s, after the first oil shock, that same blanket had found its way into civilian survival kits. It sat on shelves in every camping store across the country. $3 and 12 microns thick, it reflects roughly 90% of infrared radiation across the wavelengths our sun emits and our bodies give off. The science Maloni, measured by hand in 1831, had been industrialized, militarized, space-rated, and priced for pocket change. Yet almost none of it made its way back into the design of ordinary homes. The very film that protected Apollo astronauts on the lunar surface, the same chemistry lining every space probe ever launched by humanity, set unused on hardware store shelves, 6 blocks from your house, priced at $3.14. Why does a sheet of aluminum reflect heat? The answer lies in the metal's electron structure. In solid aluminum, atoms share a cloud of loosely bound electrons, a phenomenon physicists call an electron sea. When an infrared wave strikes the surface, it attempts to push those electrons back and forth. The electrons respond, but their natural oscillation frequency, known as the plasma frequency, sits far above infrared light. The wave cannot drive the electrons enough to absorb the energy. Instead, the energy bounces back the way it arrived. For polished aluminum in the long-wave infrared band, reflectivity ranges between 0.92 and 0.97. For anodized or oxidized aluminum, the value drops towards 0. The polish matters. The freshness of the surface matters. A wrinkled, dusty piece of mylar performs noticeably worse than a clean, taut sheet. Reflection alone is not enough. Heat moves in 3 ways: radiation, conduction, and convection. Mylar handles radiation. To handle the other 2, you need an air gap behind the film. Precision is crucial here because this is the step most guides online get wrong. Almost every tutorial says a wider gap is better, 5, 6, 7 centimeters between film and glass. Physics says otherwise. Below about 12 millimeters, air in a vertical cavity remains still, conducting heat poorly, which is what insulates. Above roughly 20 millimeters, gravity pulls cold air down one side and pushes warm air up the other. A convective loop forms, and the gap stops insulating, instead moving heat. Published research on double-pane windows, from the journal Energy in Buildings to the ASHRAE A Handbook of Fundamentals, identifies a sweet spot of 15 to 20 millimeters, half an inch to 3/4 of an inch, refined quietly over 50 years by manufacturers. Almost no DIY guide mentions this. Returning to the household window mock-up, the knowledge that was carried and quietly lost for 4 generations begins with Maloney. Reflectivity tables of polished metals were once standard in physics courses, and their practical use appeared in builder manuals. Apprentice carpenters in farm states copied them into pocket notebooks. Architecture programs taught them alongside masonry and timber framing. Since central air conditioning became standard in American construction, the tables drifted to the back of textbooks or vanished entirely. Most of us never knew they existed. The number Maloney recorded in a Medina basement remains correct. We just stopped passing it on. If your family lived rurally before about 1955, you might still find it in the attic of a house you grew up in, craft paper backed with thin aluminum foil stapled between rafters or joists, foil facing down into the dead air space above the ceiling. Your grandfather, great-uncle, or the contractor who built the house placed it there because someone taught them what Maloney measured. They didn't call it a radiant barrier. They called it foil-backed paper, insulation board, or simply silver stuff. The principle remains the same. You can stretch it across a south-facing window tonight for less than the price of a coffee. The knowledge didn't disappear because it was disproved. It vanished because those who carried it were no longer asked. The reason no one talks about this is structural, not sinister. Nothing in this story can be patented. Radiant reflection physics is public domain. Aluminum foil is sold by the kilometer. Core patents on aluminized polyester film expired decades ago. No startup with $1 billion valuation is built on a sheet of mylar because the science cannot be fenced. Without ownership, there is no recurring revenue. A homeowner who tapes a $3 sheet to a window will not buy another for a decade. Contrast this with central air conditioning. A new unit costs $4,000 to $6,000. The compressor draws $30 to $60 a month in electricity through the cooling season. Refrigerant recharges every 3 to 5 years. A full mechanical replacement occurs every 12 to 15 years. The lifetime cost of cooling one room in an average American house ranges from $12,000 to $25,000 over 30 years. The lifetime cost of a mylar window treatment replaced once a decade is under $30. That asymmetry explains why the cheap solution drifted out of conversation. There is no marketing budget for foil because there is no margin. There are no industry-funded studies because there is no industry. Money flows where there is friction, and there is no friction in $3 film. 2 verifiable tests exist in the public record. The first is the Torrent Research Center in Ahmedabad, India, a pharmaceutical complex designed by architects Nimish Patel and Parul Zaveri, completed in 1997. The main blocks operate without mechanical air conditioning, pairing reflective and high-mass external surfaces with passive downdraft evaporative cooling towers, the modern descendants of Persian wind catchers and Egyptian Malkaf. The first year of monitoring, published by Brian Ford and colleagues in Renewable Energy in 1998, found internal temperatures 10 to 15 degrees Celsius below peak outside, roughly 18 to 27 degrees Fahrenheit. Annual energy savings versus a conventional HVAC reference building reached 64%. A capital cost premium of about 4% was paid back in the first year. 28 years later, the building is still in service. The second is the Phoenix case from our opening. The 18-degree differential between the treated bedroom and the untreated one sits at the upper end of what physics allows in dry Arizona air, but aligns with U.S. Department of Energy field measurements on attic radiant barriers, reporting surface and air temperature reductions of 15 to 25 degrees Fahrenheit on south and west-facing assemblies in hot, dry climates. The trick is not magic. The trick is following Maloney's notebook, respecting geometry and convection physics. Here's the protocol in plain terms. First, identify the right windows, south and west-facing in the northern hemisphere. Skip north-facing glass. Solar gain is minimal. Second, decide outside or inside. For single-pane glass, either side works, but inside is easier and lasts longer. For modern double-pane, low-E, or factory-tinted glass, place Mylar on the outside, pressed against the inner surface. Ordinary annealed float glass may crack if heat is trapped. Cracks form perpendicular to edges. Tempered safety glass is essentially immune. Old single panes are fine on either face. If unsure, install on the outside for zero risk. Third, and this is where most online tutorials fail, build a frame, not a flat sticker. Maintain an air gap of roughly 1.5 to 2 centimeters between film and glass, not 5 or 7. Foam weather stripping sold for door seals. Applied continuously around the window perimeter creates the gap with no measurement. Stretch Mylar across the foam, pulled taut by hand. Wrinkles cause local hotspots and accelerate degradation. Fourth, seal every edge. The gap only works if hermetic. Use aluminum foil tape sold for HVAC ductwork, not masking or painter's tape. Run tape continuously with no breaks. Even a small slit invites convective bypass, collapsing insulation. Fifth, measure. Place a $4 indoor thermometer on a shelf away from direct sun before installation, and again 3 hours after. Compare readings against an untreated room. That data is the point. Limits are clear. This works best in dry heat. In humid climates, much of Southeast Asia, the U.S. Gulf Coast, the Caribbean, southern China, the radiant component is smaller, and Mylar alone will not cool the room. Humidity must be addressed with dehumidification or controlled ventilation. The film does not block conduction through frames or air leakage. Rotten frames must be fixed first. Mylar is opaque. The view is sacrificed for the cooling season, and its appearance is unmistakably silver. None of this is fatal. All of it is honest. Maloney took his last measurement in 1854, weeks before cholera reached his town. The reflectivity of polished aluminum has not changed, nor has the equation. What changed is who remembers it. Tonight, your south window, a roll of film, foil tape, 90 minutes of work, a thermometer at 4 p.m. and again at 7 p.m. Compare the room you treated to the room you didn't. Record the difference in the city. That is the only field log this knowledge has. Whether the next Phoenix heat dome finds you ready depends on how many of us write down what we measured. Please leave your thoughts about this content in the comments below. Thanks for watching. See you in the next one.